Swayam Prabha. Digital India. Educated India.
Welcome back. So, today we will continue from what we were discussing in the last class. If you remember, we were talking of distribution, breadth, or also known as spread factor. Do you recall it? I mean, something important we had done last time. The idea was that if you have let us say concentrated winding here, okay. So, all the N turns are let us say concentrated here, then if the EMF per turn is E t, then if all the all the turns are concentrated in one place, and like this we have N turns here, then the net EMF which will be generated will be N times of E t. But then what happens here? The space which you see here, this space is not utilized. That is one thing. The other thing is, when I will do the derivation of the rotating MMF very soon, you actually want B to be distributed in space in a sinusoidal way. That is something we are very keen about. So, as I had said earlier also, this will create, if you concentrate like this, it creates flux patterns which will look like this somewhere, and this kind of patterns are if you look at this kind of patterns, they are not very comfortable because they have fundamental plus many harmonics involved in them. So, lot of harmonics will come in them when you do the Fourier series. And see this thing which says that this B of theta is going to be B1 let us say cos of theta plus let us say B3 cos of 3 theta, some even harmonics are not there, I am assuming for the time being, and so on, B5 cos of phi theta and so on. So, if they have this kind of a B theta is distributed, and let us say this is on a magnet for which is rotating, like in a synchronous machine. Instead of right now talking of winding, say that it is on a magnet, the magnet is somewhere sitting here. Because the winding should be closed. So, I am just closing this, winding is closed. So, you have the stator, you have the stator on which the winding is there. This is the rotor which is, let us say, rotating in the anti-clockwise direction at a speed omega. So, this is again, remember, a two pole machine which is also called as alternator or a synchronous generator, whatever you want, whatever names you have given to them. Each of them imply different things. Alternator means it is generating alternating voltage. Synchronous generator means it is a synchronous machine. That synchronous word comes from the fact that in the grid all machines have to rotate at the same speed. That is very, very important, otherwise the grid will not work. So, all AC machines in the grid are always running exactly at the same speed in the steady state condition, and if there is a disturbance which causes them to sort of oscillate with respect to each other, then the damping in the system will usually be such that after some time they will again come in sync with respect to each other. And so, it is like a ballet dance in which all of them are nicely synced up. So, that is why this is called a synchronous generator, and these machines are in basic synchronous electrical machine is a reversible machine. You can put in mechanical power and get electrical power out. You can put in mechanical power, get electrical power out, that is the generator action. You can put in electrical power, get mechanical power out, that is the motor action. So, but when you say synchronous machine, the speed is always the same, corresponding to 50 hertz. So, if I, for example, look at a torque speed characteristic of a synchronous machine, and this is the speed of the synchronous speed 50 hertz for a 50 hertz or whatever. Instead of saying 50 hertz, let me say 3000 RPM 50 into 60 for a two pole machine. If it was a four pole machine, it will be 1500 RPM, and if it is a six pole machine, then it will be 1000 RPM. So, the multiplier factor is basically, I had explained this also to you in the some of the previous class, that the B waveform, the mechanical spread is only 360 degrees. If you are having only one pole pair, 180 degrees you get for this north to south, then south to north you get another 180 degrees. But if you have two pole pairs, then you would have north south kind of a thing. So, you get so you complete one with two pole machine, you complete one north to south, south to north. This 360 degrees covers one south to north and one north to south and one south to north, which is basically one cycle or coming back to the original position. Here that happens only in 180 degrees, north to south, south to north happens in only 180 degrees mechanical, but this is equivalent to 360 degrees electrical, this is also equivalent to 360 degrees electrical, because you are back to the north pole, that is the idea. So, therefore, if P is the number of poles and so P by 2 becomes the number of pole pairs, and if theta is the mechanical angle, that means across the surface, then the electrical angle becomes P by 2 times of theta max. So, we call this as I keep revising this because it is not a difficult concept, but should we have enough clarity, and repetition brings that clarity, because different day we explain the same concept with a slightly different words, slightly different phrases, slightly different expressions, and somewhere it clicks, you know. So, the mechanical radiance, therefore, if you look at this by dt, then taking the derivatives, which means that the electrical speed also gets a factor of P by 2 with respect to the mechanical speed, but the grid is always going to run on what? Grid is always running at 50 hertz here in India, Europe also mostly 50 hertz, North America 60 hertz, but whatever it is there, that one frequency is not going to change. So, this means that this is equivalent to 3000 revolutions per minute. So, if this is 3000 revolutions per minute, then the actual RPM, n revolutions per minute, that we require, if P is taken to be 4, then it will be 1500. This comes from this is 4, this is 4. So, this is 2. So, 3000 divided by 2 is going to be 1500 RPM. If I take P as 6, P by 2 will be 3, 3000 divided by 3 will be 1000 RPM, and if I take P as 8, then it will be 3000 divided by 4 or 750 RPM. If I take P as 10, then it will be 3000 divided by 5 or 600 RPM. Now, on the higher end here we have thermal generators. The steam turbine, the steam impinges at a very on the turbine, from the steam is produced in the, there is a boiler, then there is a water, then water is heated to steam, in fact it is superheated, it comes to the nozzle, it exits from the nozzle with a very high velocity, it causes the turbine to run at a very high speed, which is 3000 RPM. We run that by the speed control mechanism at 3000 RPM, and that is really a high speed machine. So, I had mentioned to you that its rotor should be cylindrical, its winding has to be distributed, and this has to be one mass, because otherwise at this high speed the centrifugal forces will cause things to fly away. So, this is the rotor and this is my air gap. Stator, this is north south. So, this will be dots, this will be crosses, process means current is going inside, dot means current is coming out. So, if I run it like this, north to south, it moves in your direction. So, I get this as the north pole. So, the B lines will, sorry for my poor sketch, but the B lines will look like this. And then I have a winding, say, sitting here, and this north south is rotating. So, there is a rate of change of flux in the winding, and that rate of change of flux will create a EMF per turn, which is 4.44 F and phi, where phi is the flux created per pole by the machine. I think we have derived this expression earlier, and we will this is rotating and this is this thing. But then, as I said earlier, I mean later on, if I am at the hydro level machine, and as more and more, see, thermal machines basically create pollution also, right. So, they are, over a period of time, they are going to be decommissioned, and they will be replaced by PV and wind turbines. So, these will be our future green resources. There is a possibility that you will also have nuclear, because nuclear also is not emitting CO2, even though it has a radioactive waste issue. You can properly seal that radioactive waste and store it somewhere. So, otherwise you have to, of course, with thermal machines also you should do probably a carbon capture and all those kind of things, that makes it expensive. A PV or the trend is towards PV, wind, onshore, offshore. India right now does not have any offshore farms, but in future it will have, hopefully it is going to have more offshore farms also. So, they will complement the PV the PV or the solar has a drawback that it is there only in the daytime, it is not there in the night time. Of course, both of wind and solar are infirm generations. So, which means to say that if only the sun shines, it will generate, if only the wind comes, it will generate. But and the wind machine could be a synchronous machine, wind machine could be a induction machine, which I am going to discuss the next thing after I have finished with windings. I am going to discuss induction machines only. And but the point is, hydro machines will also stay. Now, nuclear will also run as they will also create, basically the coal firing is replaced by a nuclear fission reaction, and that generates controlled, of course, and then that generates heat, and then you create steam, and after that the principle is more or less same. So, thermal or nuclear generators will be this, but when you come to the hydro machines, they will have typically pole pairs like this, many, they are huge machines, very large number of pole pairs. They are down below in the valley here, somewhere here is your reservoir, and then there are these pipes or whatever running, which carry, when you open the gates, you control the flow of water. Then this water comes at a high velocity, of course, not like the steam, high pressure steam which is released from the valve, but still it comes at high velocity, and then it hits on the turbine and the turbine blades. So, if there is a turbine like this and the water hits like this, it will go down and it will come up, and it will, this turbine will rotate, and when it rotates, to this is connected the shaft of the generator, electrical generator, and then that electrical generator will rotate. But the speed of the rotation will be, mechanical speed of rotation would be much smaller, like 600 RPM or something like that, and then to get it back to 50 hertz, you will need to have many poles, like north, south, north, south. Now, these, because the poles, these are like multi-pole machines, you cannot have it on one rotor and this construction will not work. Instead of that, you will have them as the salient pole machines, but because the speed is low and the centrifugal force mv square by r is therefore going to be much smaller, m omega square r or mv square by r is because the speeds are smaller, the centrifugal force is going to be smaller. So, the construction is going to be manageable. So, the important lesson that we have to we have to learn is this d this is number 1, this is number 3. Now, this in the space in 1 360 for a 4 pole machine, in for 1 360 degrees mechanical, suppose this is 1 360, this is a 2 pole pairs or effectively 4 poles. Let us say this is the, let us say this is B versus theta, assuming that you are able to generate a sinusoidal waveform. So, this is my B. So, this is 360 degrees mechanical, this is 360 degree electrical. This comes with the 2 pole pair machine. This is comes with 2 pole pairs, not 1 pole, means 4 pole machine. Let me not confuse you. Let me just say this is my 4 pole machine. This is how the space distribution of flux will, this is how the space distribution of flux will look like. Now, if this is the way the space distribution of flux is looking like, if I had this is mechanical. So, this is 180 degrees mechanical. Now, if I gave you 6 pole machine, and then we will come back to something else that I want to discuss, but let me just do that this once. So, 360 degrees mech will, sorry, what is my P by 2 theta mech is equal to, P by 2 theta mech is equal to theta electrical. So, if I have 360 degrees of mechanical and P by 2 is going to be 6 pole machine, so into 3. So, this is going to be 3 times of 360. 3 times of 360 means 1 360, oops, 1 360, next 360, next 360. So, I will finish in this 360 degree mechanical, this is 360 degree electrical, next is 2 into 360 or 720 degree electrical, and then 3 into 360 or 1080 degrees electrical. So, the space distribution of B theta versus theta will look like this. I will cover 3 cycles. So, that is why if I want to generate if I want to generate if I want to generate 50 hertz waveform, then I should rotate it at 1/3 of the speed of 3000 rpm, or in other words I should rotate it at 1000 rpm. Now, look at the same problem. Now, look at another angle to this problem, another perspective. This perspective is this perspective is like this. I told you that let us for the time being look at only 2 pole machine, okay. Simple 2 pole machine, let us look at it. And I have told you that in this cos theta or sin theta I write it, that depends upon where I place the theta equal to 0 axis. The waveform is basically like this only, whatever is the a periodic waveform, it keeps repeating itself. Suppose it is a sinusoid, if I put t equal to 0 where the b starts increasing from 0 onwards, that is a sine wave. If I put t equal to 0 at the peak, then t equal to 0 or theta equal to 0, depending upon whether the x axis is theta or x axis is time. If I put it where the peak is, then what happens? It becomes a cosine waveform. So, frequency resolution, whether it is odd harmonics or even harmonics, means odd harmonics means third harmonic 3 times of the 50 hertz or 5 times 50 hertz, or whether it is a even harmonic, that is nothing to do with that is a different problem which has got to do with the shape of the waveform. But whether it is sine or cos, that means sometimes I can write it like this also. This is what a typical waveform will be, then it will, I can have sine or cos, that just depends upon where I put the theta, but this is to say that this is the third harmonic. So, what I am trying to sort of say is this is the third harmonic in space, and this is fifth harmonic in space, space harmonic also it is called. This is fundamental, and there is no DC because it is there is north south poles will always come in pairs. So, because the north south poles always come in pair, so you will have fundamental, and then there is no DC component which is going to come with it. So, now if the look at it this way, third harmonic will complete three pair of cycles, three pair of 1, 2, 3 pair of cycles in one rotation, and this machine is rotating at 50 hertz. Then what is the harmonic frequency? 50 into 3. So, the third harmonic will generate a waveform if this B has a third harmonic component, if B of theta has third harmonic component, then if B of theta has third harmonic component, it will generate a waveform which is at 150 hertz, and fifth harmonic will generate a waveform which is at 150 hertz. This is the waveform, means induced voltage terminals. This is the waveform that it will generate at 50 hertz, and this distortion we do not want to have. This distortion we do not want to have, and to control this distortion, we short pitch the winding. So, this is the next concept that we are discussing today, which is the short pitching of the winding. So, let us say that a pole pitch is what? Electrically it is 180 degree. So, when I go from north to south electrically I cover 180 degree. So, let us say this is my this is my, let us say uh, this is my one pole pitch. This is what we have been doing. We have been putting the two opposite conductors 180 degree apart. So, their EMF when we join them in series. So, their EMFs are exactly in phase and they add, and then they so if there are n turns in this particular slot, you will get that much of addition there. Then if after this, if the next one, and after this if it comes here, the next slot comes here and the next slot comes here, then that EMF is slightly displaced by that angle alpha which we talked of in the last class, and then therefore, the next voltage comes like this and then the next voltage comes like this, and we did this netting last time considering this phase distribution and came up with the distribution. We came up with the distribution factor in our last class. But what I am now talking of is basically that you see, because of the because of the harmonic space harmonics, this is usually called as space harmonics. What I am talking of is space harmonics in B of the magnet, which is also your rotor, leads to corresponding, that means at the same frequency, corresponding voltage time harmonics, I will say now just for the sake of time harmonics in voltage. So, the third frequency space harmonic will lead to 3 times 150 degrees harmonic in the voltage, and this we want to these harmonics, our end goal is that we want to eliminate or restrict from where? From the terminal voltage. And how do you do it? One is you cut down, you reduce the space harmonics. So, I have talked of how to talked very roughly that mechanical construction should be should be avoided, can be improved. The gap should, you know, where the B is maximum at the pole face. If there is the gap here, then you take like this, then you taper it down. I will illustrate it to you. You taper it down. You do something like this. In the mechanical construction, you can do something like this. If this is, let us say, my stator side, and this is a 90 degrees distribution, 90 degrees, half of the pole pitch I am showing. Let me break it into some equal number of sections, 1, 2, 3, 4, 5, 6, and let us just shade it a bit. Now, what I do is, if rotate it a bit slightly. Yeah. So what I do is, I keep, let us say, a gap of Lg, let us say this is my air gap Lg here, then I keep it like sort of steady or at something like this for 2, then from 4 to let us say 2, I taper it down further. So, it is increasing now. Now, you see this is increasing, and suppose this is where the or I taper it down up to say 1. I taper it down up to 1 like this, and then I have for 0, that is where it should come to 0, I set it like this. So, if this is say Lg, then if I want to plot the B waveform like 0, I am expanding it here now 0, 1, 2, 3, 4, 5 and 6, and say this is 100 lines of flux are let us say somewhere here, then it remains sort of, means it is angled a bit properly. So, that it is Lg here, it is Lg here, it is Lg here, slight angle is there, the curvature is matched. Then I get for up to 4 I get something like this, and then because the taper is increasing, the B will keep reducing, the number of flux lines will reduce in inverse proportion to, so it will be 100 into Lg by L. So, the inverse relationship is there, as this increases, so will this reduce, and then I will get to the 0th, I will get to the 0th place, and so if this is marked as B6, this I mark it as B5, and if I mark this as B4, B2, B1 and B0. Now, ideally, because this is where it has to, it should be 0, right. I mean, if this is my north pole and this is my south pole. So, when I hit here, the B has to become, the lines of flux have to go like this. So, therefore, the B should be 0 here. So, what I have to do, sorry, what did get pasted? So, what I have to do is, I have to treat this as actually, so I will rub this. What I have to do is, I should treat from where it started reducing, this should have been reduced to 0. So, whatever is remaining, I will treat it as it is a leakage which does not, flux leakage which does not go to the winding. It is a flux leakage which does not go to the winding. So, actually it is something like this. This is B3, this is B4, this is I am sorry B3, B2, B1, and this is where the 0 will come. So, this is my salient pole gap flux gap density distribution. This is what is my this one, and if I do some more work on it, then I can show that this will give me a B1 like this. This is the space proper sinusoid, and then I will get B3, B3, this is 1.5. B3 means this space harmonic is in one is if this is like 1.5 in the, if this is 90 degrees, then this B3 will be 1.5, and similarly then you will have B5 and I am sorry B not B3 will not be 90 degrees. So, this is quarter, right. So, 1/4 of it. So, the B3 should be only this and this 3 times of multiplication factor. So, this will turn out to be B3, and B5 will be something like space harmonic B5 will look like this, and B7 would be, you notice one thing specially, I am sorry, you notice one thing specially that the it is not come out that well, but it is okay. It's okay. You notice specially that this will be B7 something not exact, but you notice something that amplitude of it also keeps reducing. So, that is why this usually this B3 will be like, for example, 1/3 at least of B1, B5 usually you can sort of assume that magnitude wise, max values wise, these are the peak values wise, they will keep reducing. So, the harmonics are there, but if the harmonics become more than the, if they do not reduce with respect to fundamental, then there is going to be a problem, right. They should not increase, they should in fact reduce. So, that the reduction basically indicates that whatever we are doing is closer to ideality. These are approximations, these are aberrations, they are small, and higher level harmonics they become smaller. At some point of time we can ignore them as far as our analysis is there. But if for example, I could eliminate the third harmonic, if for example, I could eliminate something by which is what I am now going to discuss with you, that if by short pitching I could eliminate the third harmonic, that much better, and if I do that something like that, it should usually help also for the fifth harmonic and so on. So, my third harmonic voltage, my waveform will come closer to ideal sinusoid. So, short pitching is basically done to do this. Now, let us understand the concept, short pitching concept clearly. The motivation we have got pretty well. Let me copy this. Let me paste this here. Now, what I will do is, I will now assume, I will just modify this figure a bit, and I will assume that this is my one pole pitch. Okay. This is usually done with a two double. This is usually done with a what I mean to say two layer type of winding. So, this is one pole pitch mechanically, that is constructionally, and I have sort of short pitch coil. So, I have reduced it by 1. So, what will happen now is that if I look at if I look at the EMF now I cannot directly talk in terms of EMF of a coil like what I was doing earlier. I will talk of EMF of this conductor 1, and see this conductor, they were exactly in phase. The way I did the series connection of the winding, they were exactly in phase when they were one pole pitch apart, and you doubled it basically, right. So, I could, that was the idea. But now if, so it was exactly twice when pole pitch apart, I am sorry, when pole pitch apart, these EMFs were in phase and I could just add them together. Now, what is going to happen, because I have short pitched it, if this is my EA, the EB is not going to be here, but EB will be somewhere here. This is my factor beta, and the EB factor beta is this degree, this angle in electrical radians. This for the one slot, the angle in the electrical radians, that is my beta, and so the EMF induced in the coil is now going to be a vector summation of this. So, this angle is, let us change the color, this angle is beta by 2 by symmetry, this angle is beta by 2, and so this distance is EB or EB or EA, whatever you call it, EA cos of beta by 2, and so this will be 2. So, this distance here, this is EA cos beta by 2, this is also EA cos beta by 2. So, 2 EA cos beta by 2 is the actual net induced EMF, but if I had not done this short pitching, then I would have got 2 EA. So, therefore, this factor is known as the pitch or coil factor, pitch or coil span factor is basically cos of beta by 2. And what is that factor? This factor, also shown as Kp, is the EMF with short pitched coil divided by EMF with full pitched coil, and this is cos of beta by So, if earlier we had talked of the factor distribution factor K d, now we are talking of pitch factor K p, and if the number of conductors are Z, the number of conductors are Z, then the induced EMF is going to be equal to RMS value of EMF per phase is going to be equal to 2.22 kd k phi kd k phi into f into phi. So, both of these factors will have some effect in reducing the net RMS of the voltage. So, this part was this is the effect on the fundamental. Now, if let us say we are talking of harmonics. So, let us say that now I am talking of harmonic voltages. Now, I have already told you here earlier somewhere that this space harmonics basically give you a multiplier effect of n here, 3 times for third harmonic, 5 theta for the fifth harmonic and so on. So, therefore, space harmonics will be attenuated by nth space harmonic will be attenuated by cos of n beta by 2. So, therefore, Kp of n is going to be attenuated by cos of n beta by 2. So, this should give you some idea about what exactly we are trying to do. For example, suppose that this beta is 30 degrees. So, that means I have 6 slots per pole. I think this is, I hope this is correct, 6 slots per pole per phase. So, one pole is equivalent of 180 degrees and 6 slots per pole per phase. So, in that case, basically let me not worry right now just about this. Basically, between the two slots I have a 30 degree angle, that is what is the most important thing that I am trying to say. This is also called as the chording angle, some places it is also called as the chording angle. So, then what will happen is I will get a factor of cos of 30 degrees by 2 or cos of 15 degrees for which is equivalent to 0.966. So, therefore, if I write here the harmonic order, harmonic number or number n, and if I look at the span factor or if I look at the coil span factor or pitch factor, and let us talk of fundamental here. So, fundamental is 1, I get 0.966. If I look at the third harmonic, then what will be it be? Cos of 3 into 30 degrees by 2 or cos of 45 degrees, or I will get a better attenuation I will get a better attenuation of third harmonic, which they will be attenuated faster. So, I will get 0.707, and if I look at fifth one, then it is cos of 5 into 30 degrees by 2, cos 90 is 0. So, cos 75 degrees comes even more closer to 0. So, I get 0.259, and then for interestingly seventh, if I look, cos of 7 into 30 degrees by 2. So, this is going to be cos of 15 into 7 is 105 degrees, which is cos of which is cos of. So, this is 90 minus 15, and this is 90 plus 15. So, magnitude point of view, this is again going to be same number. If this is say 0.259, then this is also 0.2559, except that the cos 90 minus 15, one is going to be positive, another is going to be negative, and then the ninth one will of course come back to, you see the cycle, it will come to actually minus 0.707 on the other side, but I will write it as magnitude point of view, it is going to be 0.707. So, what happens is this way, by properly short pitching, I can attenuate the time harmonics which are coming in the induced voltage waveform due to space harmonics which are created in the B waveform, and this is the main advantage of short pitching here. We will do some examples in the next class. Thank you.